Okay, Bismillahirrahmanirrahim. Dear student, today's topic is binding energy and nuclear stability. And its further subtopics are, these are all the subtopics of binding energy. Maximum and minimum peaks in the binding energy, why they are coming, and how the lowest elements which type of energy they will give, which type of process will be generated, and like release of nuclear energy and fission and fusion. Then you will see that if lighter nuclei and heavier nuclei, in both cases you will see the fission and fusion process. As we know that binding energy is energy required to break a nucleus into its constituent nucleons like protons or neutrons. Now you see from binding energy curve, which has already been drawn, along x-axis mass number is taken, while along y-axis binding energy per nucleon is taken. This binding energy curve explains us that some of have a very high binding energy and some of it have a very low binding energy per nucleons. Why it is so? It will be also explained in this lecture, inshallah. We know that binding energy per nucleon of the deuteron is, binding energy of the deuteron is 2.23 and nucleon mass number is 2, so we will get 1.11 MeV. Thus it is very loosely bound system. Why it is loosely bound? Because the energy, binding energy per nucleon is too much low. It is too much low. The binding energy of the nucleus gives the quantitative measure of its stability. Means, for example, those elements which have a high binding energy, they are most stable, and those having a less binding energy, they are less stable. Now consider the nuclide He24. He24 is basically helium nucleus mass of alpha particle, which is made of 2 protons and 2 neutrons. In the helium nucleus C, proton number is 2 and neutron number is A minus Z, that is equal to 4 minus 2 is equal to 2. Yani He24 is consisted of 2 protons and 2 neutrons in the nucleus, whose binding energy comes out to be 28.299 MeV. Binding energy mass defect, इससे पहले हमने किया था ZMP plus A minus Z into Mn minus mass of nucleus, ये किया था. अब according to the equation E is equal to delta mc square, multiply the mass defect with c square, you will get the binding energy. The binding energy of the deuteron helium nuclei, which comes out to be 28.299. How it is coming? You will put mass of proton, how much it is? 2 multiplied by mass of proton in atomic mass unit, and 2 is the number of neutron, multiply it with the mass of neutron, and mass of the nucleus will be given, He24. This will give you mass defect. Now multiply this mass defect with 931, you will get the value 28.9299 MeV. In last chapter I have done it. This is a huge energy, 28.299 MeV. In other words, the energy required to break up He24 nucleus into its constituent nucleons, we must spend about 28 MeV of energy. In order to break the helium nucleus, which is a binding energy 28.299 MeV, how much energy is required? the energy in this case, in order to split this helium nucleus into its constituent nucleon, that is proton and neutron, you must supply 28 MeV energy to the nucleus, because the binding energy of the nucleus is 28.299 MeV. So this amount of energy will be required to break the nucleus, helium nucleus, or the alpha particle. Thus the binding energy per nucleon for helium nucleus is about 7 MeV. If you see binding energy per nucleon, binding fraction is binding energy per nucleon, that is E binding divided by its mass number. If you divide 28.299 with the 4, this will become round about 7 MeV. The binding energy per nucleon for helium nucleus is about 7 MeV. That is round about 7 MeV. This one is round about 7 MeV. Greater the binding energy, more stable is the nucleus, like He2, beryllium, carbon, etc. He2, this is beryllium, carbon, oxygen, etc. That is why sharp peaks are coming. Those nuclei which has a high binding energy, you will see from the curve that sharp peaks are coming because of the high or more stable nucleus. There is a sharp increase in binding energy. There is a broad spectrum, maximum spectrum. In the mass number 40 to 120, if you see here, then from 40 roundabout to broad spectrum, you are getting from 40 to how much? From 40 to 120. In these nuclei are stable one, and its average value of 8.5 MeV. In those nucleus which has a mass number of A is equal to 40 to A is equal to 120, they having energy round about 8.5 MeV. This is a very high energy, binding energy per nucleons. So it is coming around about this to this value, 120 suppose. The maximum value of binding energy per nucleon is 8.8 MeV for mass number A is equal to 60. Thereafter binding energy per nucleon falls to 7.4. यानी आपने देखा कि ये किस तरह एक्सप्लेन होता है, ये बाइंडिंग एनर्जी करो तो आप देख रहे हैं कि मुख्तलिफ पीक्स आ रहे हैं, बाज़ इसमें राइज आ रहा है, बाज़ इसमें फॉल आ रहा है, और बाज़ स्पेक्ट्रम जो है तकरीबन एक जैसा आ रहा है. तो मैक्सिमम वैल्यू जो है बाइंडिंग एनर्जी पर न्यूक्लियन का वो है 8.8 MeV. दैट इज़ दी mass number A is equal to 60, element which is getting mass number A is equal to 60, that is giving you 8.5 MeV. And after that you see it, the graph, if you see the graph, from the graph you see that after that the binding energy curve fall or it is decreasing it is falling or it is decreasing. So it means that maximum value of the binding energy per nucleon is 8.8 MeV, and the majority of the nucleon having binding energy per nucleon 8.5 MeV. And later you see, after that, if the mass number increases, the binding energy per nucleon also decreases. Now I am going to explain why the peaks are coming in the binding energy curve. There is a rise in the graph and then fall in the graph, maxima, minima you are getting. The 5 peaks in the binding energy curve correspond. How many peaks? For example, this is 1, 2, 3, 4, इधर चौथा 5 दूसरा भी होगा नियान का. What it shows? This shows that the nuclei having an even number of protons and even number of neutrons, and they do not have any unpaired nucleons. If you see He24 proton, P is 2, this is even, a neutron is also even 2. Similarly, in beryllium, there is proton 4 and neutron 4. And carbon, there is proton 6 and neutron are 6. So it means that those nuclei which are of even number of protons and neutrons, they are much stronger and having a high binding energy and are stable one. That is why I have written here the nuclei have an even number of protons and even number of neutrons. That is, they do not have any unpaired nucleons. These nuclei are therefore more stable than their immediate neighbors. In immediate neighbor, here you see, this is immediate neighbor, this is immediate numbers. Why there is a fall or minima we are getting in lithium, beryllium, and so on? The reason is that in lithium Li3, the number of proton and number of neutron are not equal. They are having odd number. So they are getting unpaired nucleons. While in case of helium, beryllium, carbon, oxygen, etc., they have a paired nucleons. Due to its pair formation between the nucleons, these nuclei are much more stable. While the nuclei, the immediate nuclei, which is helium, immediate nuclei, after helium is lithium, beryllium, and so on. These nuclei have unpaired nucleons. The beryllium, the binding energy on either side of these nuclei fall abruptly due to the unpaired nucleons and hence giving rise to a minima. 1H1 आपको मिनिमा आएगा, लिथियम में मिनिमा आएगा, बेरिलियम में मिनिमा आएगा, एटसेट्रा. तो इसलिए ग्राफ जो आप लोग देख रहे हैं, तो उस ग्राफ में जो कि प्लाट किया गया है बाइंडिंग एनर्जी पर न्यूक्लियंस और मास नंबर के दरमियान, यू सी इसमें मिक्सिमा भी आ रहा है और मिनिमा भी आ रहा है. तो मिक्सिमा क्यों आ रहा है और मिनिमम क्यों आ रहा है, और उसका कुछ हिस्सा जो है फिर ब्रॉड स्पेक्ट्रम दे रहा है, फिर उसके बाद फॉल हो रहा है. तो इससे मुराद ये है कि ये सारे आपके पास जो एलिमेंट्स हैं उसकी बाइंडिंग एनर्जी पर न्यूक्लियन इसकी वैल्यू सेम नहीं है, बाज़ स्टेबल है और बाज़ अनस्टेबल है. स्टेबिलिटी जो है वो आपको मिक्सिमा देगा पीक्स, और जो अनस्टेबल है वो आपको मिनिमा देगा. मिक्सिमा यानी वो न्यूक्लियाई जिसमें नंबर ऑफ़ प्रोटॉन और नंबर ऑफ़ न्यूट्रॉन वो इवन नंबर के हों, जो कि पेड हो, और मिनिमा तब देगा जब आपके पास नंबर ऑफ प्रोटॉन्स और नंबर ऑफ न्यूट्रॉन्स न्यूक्लियस के अंदर जो है अनपेड हो. So those nuclei which have unpaired nucleons, they are not a stable one or less stable, and those nuclei which have paired nucleons, they are more stable. The reason of its stability is, इधर देख के मैंने लिखे बाइंडिंग एनर्जी इन न्यूक्लियर स्टेबिलिटी, स्टेबिलिटी जो है इस मकसद के लिए है. अब हाउ द एनर्जी release of nuclear energy in fission fusion. What is fission and what is fusion? Fission जो है, it is that process in which a heavy nucleus is splitted into two nuclei with the release of energy. यानी अगर आपके पास एक हेवी न्यूक्लियस हो, वो स्प्लिट अप हो जाए, सपोज यूरेनियम U235 है और वो स्प्लिट अप होता है बेरियम और क्रिप्टॉन में, तो बेरियम और क्रिप्टॉन जो है ये आपके पास यूरेनियम के मुकाबले में न्यूक्लियस जो हो छोटे छोटे हैं, लेकिन वो चूँकि इस ब्रॉड स्पेक्ट्रम में तकरीबन आते हैं तो इसलिए आपको ह्यूज अमाउंट ऑफ एनर्जी रिलीज़ करते हैं. यानी अगर आप इसका ये पोर्शन देखें, ये वाला हिस्सा देखें, यानी इधर मैंने लिखा है कि बाइंडिंग एनर्जी पर न्यूक्लियन इंक्रीजेज विद मास नंबर ए. Explain the cause of release of energy into fusion of lighter nuclei into heavier one. Fusion क्या है? यानी fusing of lighter nuclei into heavier one with the release of energy. रिलीज़ ऑफ एनर्जी, इसको क्या कहते हैं? इसको फ्यूजन प्रोसेस कहते हैं. लाइटर न्यूक्लियाई कंबाइन होते हैं, बिग न्यूक्लियाई दे देता है, तो इसको फ्यूजन प्रोसेस के, और यहाँ भी एनर्जी रिलीज़ होती है. इसलिए अगर आप देख रहे हैं तो यहाँ आपके पास फ्यूजन प्रोसेस होगा, लाइटर न्यूक्लियाई कंबाइन हो रहा है और इसकी बाइंडिंग एनर्जी इंक्रीज़ हो रही है क्योंकि न्यूक्लियाई जो है वो बिगर आ रहा है. और इधर जो है आप देख रहे हैं कि फिर भी आपके पास हेवी न्यूक्लियस है, यानी इधर जो है जो अकर होगा वो क्या होगा? फिशन प्रोसेस होगा. जिससे कि हम देखते हैं कि हमारे पास ये बिजली जो है ये यूरेनियम से हमारे पास जो आती है, इट इज़ बिकॉज ऑफ द फिशन प्रोसेस. और सन से जो हमें एनर्जी आती है, इट इज़ बिकॉज ऑफ द फ्यूजन प्रोसेस. एटॉमिक बम इज़ बेस्ड ऑन फिशन प्रोसेस while hydrogen bomb is based on the fusion process. Thank you.